Okay, so we are today looking at chapter 2 of the Koenig and Ritchie C book. We've had some difficulties with chapter 1, but we are going to attend to those if we have any extra time at the end of this class. So what we're first going to do is quickly go over chapter 2, which you supposedly already read. We're going to check the examples. I've written some of them as complete programs, and they're also in my GitHub repository now. And then there are some exercises that I would like us to do together. So the chapter 2 is about types, operators, and expressions. What types are the, it's like a specification of what kind of information can be stored in a variable. For example, if you need all the numbers to always be positive, you could use a unsigned variable that cannot take a negative value, so you don't waste space in storing the sign. Whereas signed means that there's actually going to be always a space. The variable names, we want those to be usually all lowercase. We want them to be kind of short. We don't want to use reserved words like if and while and whatnot. And we're going to specify the type of every single variable before we put the name to it. The ranges of representation of the types, you can look those up in your reference card. So basically, what's the minimum value of a short int and a maximum value of a short int? Those are here. What's an unsigned character, what's an int, what's a long, what's an unsigned long, you can look at those here. And the floats and the doubles are in the double float limits. So that's the information that's discussed in exercise 2.1. It's a very good exercise to do, and I hope you will do it if you need a lot more practice. I can no longer be attending direct messages. I think this is Daniel and his registry again. But this stuff has to happen when we're not actually streaming, please. Section 2.3 is about constants. Like when we're making a value that will not change through the program. So it's not a variable, because a variable could actually change, whereas a constant is something that will never change. So we're going to use the define directive to make constants like we already did in chapter 1. This section simply explains it a tiny bit in more detail, what constants actually are. And it also explains how to make an enumeration constant, which is a set of, like, let's say words like true, false, yes, no, to which we want to assign integer values. If we don't specify the values, they just go 0, 1, 2, 3. Enumerations are really helpful for when you need to make variables that represent stuff like days of the week, months of the year or something, and you don't for some reason just want to use the number when you want to actually write a word. You can use an enumeration to make your code a little bit more readable. Section 2.4 is about declarations, which means that we need to say we're going to have these variables and they're going to have these types. It's also discussing the how many variables you can declare together. And if you initialize at the same time when you're declaring, please read that. Section 2.5 is about arithmetic operations. We're going to check those in Python because those are the same in Python and I don't need to compile. So the plus sign, it's just going to be the sum. Minus sign is just going to be the subtraction. The asterisk is going to be doing a multiplication. Division in C is going to work as integer division in Python. So if both of the operands are integers, your result will also be an integer. So if you divide 2 by 3, the answer will be 0. If you don't want it to be 0, you need to divide 2.0 by 3 or 2 by 3.0. If you just type 2 divided by 3, it's going to do what in Python would be the integer division. In Python, it's a double division mark. In C, it's just a regular division mark. And then we have the modulus, which is the residue when you're dividing. So 14 modulus 3, it means that if I divide 14 by 3, what's my leftovers going to be? So 14 divided by 3, it fits 3 times. 3 times 4 is 12. 14 minus 12 is 2. So this is the leftover after the division. This is a very useful thing because you can check if numbers are odd or even by checking what their division by 2 produces as the residual, which is the modulo. So we're going to be using that a lot. And that's used quite a bit in the example code I wrote for the section 2.5. Let's go to my repository. There's now a chapter 2. And this one has a code called leap. And this is the leap year code that's given in section 2.5. So if the number of the year is divisible exactly by 4, while not divisible by 100, or it's divisible by 400, then it's a leap year. I'm doing the constants here, defining a constant true and a constant false. Then I'm making a main routine. It uses the first command line argument, turning it into an integer to as a year, and then it checks whether or not this is a leap year. So compiling leap C. If we run leap C and we try to see if 1980 is a leap year, yes it is. If 2003 is a leap year, no it's not. So that's the example, my interpretation of the example in section 2.5. I'm going to type it here. Leap C corresponds to section 2.5. I would recommend at this point that you guys try to write your own programs. It's very important to notice that the codes in these sections, they're not complete programs anymore. They're not like the programs we had in chapter 1 that started with the include stdio.io.h and ended in closing the main. These are parts of programs and you're supposed to be able to build the whole program around them. In section 2.3, we're first talking about comparing numbers. I'm going to show that in Python again because it's the same and very easy. Stuff like is 4 smaller than 4, is 4 smaller or equal than 4, is 5 larger than 3, is 5 larger than or equal to 8, is 3 not equal to 8, is 4 equal to 5. So we can make comparisons that evaluate to true or false. Remember that true is a positive number in C and false is a 0. If we have many operations going on at the same time, it's important we put parentheses so we know what's going to happen. So if I have something like this, now we don't really know what's going to be going on. We don't really know until we put parentheses that what's the actual thing that we wanted. Because I might have wanted to first check whether this is true or false and then multiply it by 3. So please don't try to save space by omitting parentheses, just write them, it's clearer for everybody. And here in section 2.6 there was an example mentioning that in chapter 1 we had a code that was the code that checked the longest line. And we want to make an equivalent for loop, but without using the ands, the double ampersands to check that if this and this thing happen at the same time. So let's look at how it looked like in chapter 1. So we had a for loop that said that while I is smaller than L minus 1 and simultaneously the C that we got from getchar wasn't an EFO and it also wasn't an end line. Like how to do this without using this notation of combining conditions, which I wrote here It doesn't have the double ampersands anymore, but I've added ifs and I'm breaking the loop if those ifs are broken. So the equivalent .c that I wrote has to do with section 2.6. And it's essentially the exercise 2.2 of this chapter. 2.7 is a section about type conversions. How do we convert from one thing to another? Like if we had something that was characters and we want it to be a number. Or if we had something that was a certain kind of a number and we want it to be a different kind of a number. So of course we could use the conversions that come in the standard libraries. We have a lot of conversion operations there. Just let me find them on my reference card. I know they are here, but I can't find them right now. Here, conversions. And in this section of the book, we actually write the code of how to convert strings to integers. And I wrote it for you. It's here in my A to I, means from alphanumeric to integer. And why I didn't call it A to I like they do in the book, it's because if I try to call it A to I, modern compilers are smart enough to notice that I am talking about something that exists in a standard library. So it's going to tell me, dude, you're missing the library. So I actually changed the name. So what we're doing here is we're taking a sequence of characters stored in an array, and we want to get the number representation of that information. So let's, for example, suppose that we were giving a 4 to 9, and then there's going to be the string termination character that just says the string is over. So first my n is equal to 0. Then I'm going to start position by position looking at these things and checking if they are strings, characters actually, like digits. If I put something else here, that something else will be entirely ignored. So since 4 is a character between 0 and 9, I am going to multiply the existing n, which is 0, by 10, and then I'm going to sum the difference between the 4 character and the 0 character, which will be 4. So n will be equal to 4. Then I'll be looking at the 2. It also falls in this range. So I'm going to multiply the 4 by 10 and add a 2 to it. Now n is 42. Then I get the 9, which is also in this range. So I'm going to multiply the 42 by 10. So I have 420. And I'm going to sum a 9. Now I have a 429. Then the others are not going to be in the range between the character 0 and 9. So they will simply be ignored, because this condition is failed. None of this will be taken into account, and this routine will return a now integer 429 instead of a character array 429. Here we could just put any return value, it doesn't matter yet. So what this main program is doing is converting all of the command line arguments to numbers and then multiplying them by 2. Let's compile. Okay, so it took the 1, 2, and a 3 and it made them into numbers. It multiplied by 2 to get 2, 4, and 6. This wasn't a number, so the my A to I gave a 0. So if I put anything here that isn't a valid number, it's going to give a 0. And if I put something that ends in garbage, the garbage is going to be ignored. If it starts with something that isn't numbers, it's going to be utterly ignored. So here, this number was taken and multiplied by 2. Here, there weren't digits in the beginning, so it was taken as a 0. I made some changes to it, so let's commit it again. And also in section 2.7, there's a routine that converts text from uppercase to lowercase. That one I put to my lower. It just puts everything in lowercase. You need to read the book to understand how exactly this is working, but I gave you the code so you can maybe spend a little less time typing. Please don't just go to my code straight away. Try your own code first, because you learn by writing and testing and failing and fixing. You don't really learn by reading my code. So it's a bad idea to just look at other people's code. You only learn by writing your own code. Also in the same section, I think it's still the same section of type conversions, we have the program that works with random number generation. I brought you guys a program for that too. It's in my rand. I put some numbers in constants. You can try what happens if you change these constants. We have one subroutine that generates a new pseudo-random number. We have one that seeds the random number generation. If you are unfamiliar with random number generation, I'm going to find you some decent video about this, or we can talk about it on Discord when we're not in class. Okay, you guys are going to lose it if you read this. Let's not try to read that. This should work. Khan Academy is usually something that doesn't make my students hyperventilate. So you guys could look at this if you're entirely unfamiliar with random number generation. It's a very interesting mathematical topic, and if you're software students, you're going to run into it at latest on the 7th semester in your crypto class. Section 2.8 is about the incrementing and decrementing numbers by 1. There's also an example program here that they call squeeze. What it does is that it takes a certain character and eliminates it entirely from a string. And I also wrote it here, and I made a little program for it that takes the first argument given on command line as the character to eliminate, I think. Let's take a look at it. I think it was that way. Yeah, it takes the first argument as, no, wrong code. First argument has the character, well, the first letter of the first argument has the character and squeezes it out of the others. So let's try this. So let's get rid of all the A's in... Vamos a probar esta madre. Okay, I didn't compile the correct program. We were going to compile squeeze. There we go. So now all the A's are gone, because I said let's take an A away. If we're not taking the A away, if we're taking away a... What else repeats here? R. Let's take away the R's. It looks like this. And I think the first exercise I wanted to do together... Let's go here. Okay, the first one is hexadecimal conversion. Then we want to make a version of, let's jump here, a version of the squeeze thing that takes away multiple letters instead of just one. And then I think we need to look at the mini exercises on the website. If we have time, we'll do the exercise 2.6 as well. but I think we need to spend a little time in Python for that. Okay, so let's do the exercise 2-3 first. So instead of an H to I, we want to do an A to I, we want to do an H to I that takes hexadecimal strings. But before that, we need to make sure that everybody understands the hexadecimal system. Okay, so if I have a string ABC and it's in base 16, it actually means 2748. Okay? Now I'm going to make a poll to see who understands why this is the value of ABC. If you understand why ABC is 2748, please click on the green check mark. If you have no idea, go on the confused face. Okay, we have no idea. So we're going to actually have to go on the whiteboard. Just a second. Okay, we might not get very far in this class because nobody knows hexadecimal numbers, but we are going to try. So when someone gives you a number like 321, you're thinking about this as a decimal number, meaning that it's base 10. How do you interpret this in your head? You think it's 1 times 1, 2 times 10, and 3 times 100. Why 1, 10, and 100? 1 is 10 elevated to the 0th power, 10 is 10 to 1, and 100 is 10 squared. And if we had something like 5,000 here, the 1,000 would be 10 cubed. So if I have a hexadecimal number, if I have the same number but in hexadecimal, it's going to mean a different thing. So if instead of the 10 I have a 16, meaning this is hexadecimal, now this is going to be a 16, this is going to be a 16, and this is going to be a 16 squared. And let's pretend this isn't here so that we don't have to do a lot of calculation by hand. So now, what does this number actually mean? So we have 1 times the 16, that's easy, that's 16. No, it's still 1 times 1, sorry, because it's still 16 to the 0 is 1. So this is still a 1, this is the 2 times 16, and this is a 3 times 16 times 16. What's 16 times 16? 160 plus some stuff, I think it's 256. That sounds roughly correct. So this thing is a 32, these two together is a 33. 3 times this thing, I have here what looks like an 18, I have here what looks like 150, and then I have a 600, so I have a 750. These things give me a 40 and then a 50 and then a 1, a 51 maybe. So this looks like an 801. Let's ask my Python. 321 base 16, 801. Okay. So that's what hexadecimal means. These things, they're no longer multiples of 10 elevated to powers. They are now multiples of 16 elevated to powers. So, what on earth are the A, B, and C? When you have base 10, your digits are from 0 to 9. When you're in base 16, your digits go from 0 to 15. But since the digit position corresponds to the power to which we're elevating the base, we cannot put multiple digits in the same position. So if you want to put a 10, you put an A. If you want to put an 11, you put a B. If you want to put a 12, you put a C, etc. So it's just the alphabet taking over. So now I have A, B, C, base 16. C means 12 times the 1. B means 11 times the 16. And A means 12 times the 256. So if I sum this with this and this, I obtain the 2748 that we have on the computer. Returning to the computer to see if we're okay. No, I wrote a 12 where it was supposed to be a 10. The A was supposed to be the 10. I keep forgetting if I write CBA or ABC. 10 times the 2056, sorry. 10 times the 16 squared is exactly the number that we wanted. So, we're making another poll. Are we any better now? I will also Google you guys a tutorial on hexadecimal numbers. Or actually, you guys could just... You could maybe just look at the examples for my math class. Let's try to find some examples for my math class. But what we're going to try to do now, we're going to copy the my a to I into an h to I, because we are going to try to actually do this. We're going to try to take strings that will now look like hexadecimal strings. I'm going to skip the part of optionally starting with the 0x. You guys can add that later. So we're now expecting a string that looks like maybe A3B0 4, and we want to know that thing's value. So now we're going to have the hex strings as an input, and we're going to have the decimal numbers as an output. We're going to be calling the h to I on the inputs. This looks wonderful. And now we just need to fix this stuff here. So now we don't just go from 0 to 9. We need to also handle from A to F, because those are the extra digits here. So basically, instead of a 4, we could start using a while loop. We could make a while that repeats forever and forever and forever until we go away from there. And we could do a thing where we handle these digits separately. We're going to fix that in a little while. Then we could do an else if that could handle from lowercase a to lowercase f. And if we encounter anything that isn't any of those symbols, then we would break the loop. And we could actually just break the loop by returning the value when we encounter something that wasn't any of those digits. So if I find something between 0 and 9, I can do a similar stuff that I was doing before, because I just need to take the what's the value of the thing, and I need to be adding it. But now I won't be multiplying by 10, I'll be multiplying by 16, because we're doing hexadecimal. So when the digits go higher, they would need to become multiplied by 16. We'll check if this logic works. And if we have these guys here, we are not going to be adding the difference from them to 0. We need to be adding a 10 plus the difference from them to A, because the F needs to be a 15 and the A needs to be a 10. So we could try this stuff here and see how horribly it fails. Let's make another window. Like when you're modifying a code, you first try the minimal possible changes. If something absolutely horrible happens, then you need to fix it. So now we forgot to change the name of the routine here. So let's try some simple number like 1, 2. Okay, it tried first with the A out because it starts here from 0. We don't want it to start with the A out. We want it to start with that number. That's the first one we actually put. Let's kill this. And it never ended with the second one. It never ended with the 0. Why did it never end with the 0? Because we're never incrementing the I. So we're going to add the I incrementation here. So hexadecimal 12 means this decimal 18. Let's open a Python so we can quickly check if any of this makes any sense. So if I was given a 18 and it was base 16, no, I was given a 12 in base 16, it's supposed to be an 18. Okay, now let's try 1, 2, 3. 2, 9, okay, this is looking good. Now let's start breaking it by putting some letters there. Oh my god. Ain't I fucking clever, it's working. Except that now it's not working anymore. So 1, 2, 3, A, B, C, 4, 3, 2. This already broke. Now, who knows an explanation of why this might have broken? I'm going to open this thing here so we can discuss why this might have broken. Ideas on Discord or Twitch chat. Why is my C program doing different from my Python program? Nobody? I'm zooming into the relevant parts until we can actually start discussing this. Andres and Antonio are kind of on board. Let's see what they say. Okay, Antonio wins the jackpot here. I have written a number that's too big. Integers can only go up to 32,000 on a regular 32-bit Unix system. I'm on a 64-bit Mac, so they may go a little higher, but I should totally be using long ints instead if I wanted to be able to deal with very large numbers. So let's make the n a long int instead. And here it's not going to be a d anymore, so I think it's going to be an ld. So let's recompile this thing. Am I just supposed to call it long? Or am I just supposed to call it L? Pretty sure I'm supposed to call it LD. Let's spy on the reference card again. I know it says it's somewhere here. Constants, floats. Here. D integer, unsigned. L is a long, so it should be an L. Maybe long int and L. Invalid conversion specifier. I hate it when my stuff doesn't work, like my reference card. Argument has okay, now I understand. It's because this thing is returning an int instead of a long int. Okay, it's been fixed. Okay, let's see if we're any better now. And now we're actually matching what Python's saying, because my representation is now big enough to actually fit the number we wanted there. So now, why isn't having letters in here a problem? Because these letters are digits in the hexadecimal system. If I put letters that aren't digits in the hexadecimal system, let's put LOL. Now it just took the 1, 2, 3. The rest of it ignored because those are not valid digits. But if I just use valid digits, we should be fine. Yay! Okay. So I'm leaving it to your exercise, how we could make this maybe briefer and how we could deal with there being optionally something like this in the beginning, noting that it's a hexadecimal string. But let's put this thing in the repository. If we could just remember what exercise this was. It says it's somewhere on Discord. Pin. Exercise 2-3. Okay, another thing it would be lovely if you guys could try is making it so that it doesn't care if those are lowercase or uppercase letters. Mine is only now working with the lowercase. To the question of Anna, in base 16, the digits go until 15. So 15 would be F, because A is 10, B is 11, etc. But in general, we can check stuff like, for example, pendejo. It's a valid number as long as we take a base that's big enough to make letters like P and O also be digits. Okay, so what else were we going to do? We were going to jump here and spy on, we were going to make the squeeze that instead of just getting rid of one character, gets rid of lots of characters. So let's copy squeeze to squeeze more. And the difference will now be that it's going to take away from S all the characters that are like on a skip list. So this is the target we're processing from, and we're going to have a skip list there. So we're going to use the first argument as the skip list, and then we're going to be squeezing all of the skip list from all of the other words. Okay. Let's call the target just T, so it's a little briefer. So now what we actually need to do is the same logic of squeezing before, but we are not just looking if it's equal to C. If it's equal to anything in skip, then we have to ignore it. So we need to know how long skip is. And we should have the method for checking the length of a string. strlen from string age. Let's use that one. There's also my own implementation in one of the examples. But we're just going to use this one. Let's put it in K. The how many letters are in the skip thing. And it would actually make a lot more sense to do it here. since we need it every single time we squeeze, so we wouldn't have to count it many times. So let's get this thing, also get a parameter k. So in here, we could do a for, let's call it in here. So we can have a k that goes from 0 to n. And we need to check if that character is equal to skip position k. If it is, we're going to skip it. So we're going to reverse the logic here. And we need a variable to know whether it's going to be skipped. So let's put here an ignore. And first we always suppose that ignore will be false. We're not ignoring anything. We need the definitions of false and true. So we suppose we are not ignoring it. If we do find it on the skip list, we do start ignoring it and we stop looking because we already know it has to be ignored. Then, if it's not going to be ignored, we actually keep it on the string. And if it was ignored, then we don't keep it on the string, we overwrite other stuff on it. And now I'm not copying stuff from one string to another. I'm like moving the characters I want to keep forward and putting them on top of the characters that I wanted to ignore, because I have two different indexes going. I is the position that I'm looking at, and j is the position at which I'm storing. And every time I store, I advance the j. So let's see how poorly I've broken this now. So now we're going to try to squeeze more. We're ignoring all the letters in a hola. Okay, so obviously the entire word hola disappeared. From mundo, we lost the O because it's in hola. From estoy, we lost the O. From probando, we lost both O and A. Que, we didn't lose anything. Tanto, we lost the A and the O. Lo, we lost it entirely. E, we lost the H. Roto, we lost the O. So it seems to be working wonderfully, and we will add it. Squeeze more into the repository. And squeeze more was exercise 2.4. No, not point. 2-4. Okay, we have 1 hour left, and I wanted to look at this bit arithmetic thing with you, and I would really like to have a little while at the end to do like a crude version of homework 1 for those who couldn't do homework 1, so you can see how that was supposed to be done. So let's try to rush through this, look at the 3 little exercises, talk about homework 2, and then proceed to homework 1. Okay, so we have one more thing. But I first want to show you guys stuff on Python. Let's hide some windows. So actually I'm going to need the Discord back to check this. Since we didn't know hexadecimal numbers, I am now slightly scared that we don't actually know binary numbers either. So let's make a poll. Green checkmark thingy if you understand binary numbers. Confused face if you really don't and you need me to explain it. Okay, so most people don't really understand. No, Diego, in hexadecimal, the case doesn't matter. Lowercase a and uppercase are the same thing. So you can just actually use like the lower routine to force everything to lowercase before you make the conversion, and it should work just fine. Okay, I'm gonna go back on the whiteboard, and I hope you guys are gonna notice that this is an obvious thing. So now remember how here the positions were powers of the base. In binary the base is 2, so the digits are only going to be from 0 to 1, because remember in base 10 we had digits until 9, and in base 16 we had digits until 15. So now our numbers are just going to look like this. Just zeros and ones and nothing else. And this blue isn't very good. Let's change it to another blue over here. So now this is a base 2 number. So again, we need to imagine the powers. 0, 1, 2, 3, 4, 5, 6. And now these are powers of 2. So this means 0 times 1. 1 is 2 raised to the 0th power. 1 times 2. 0 times 4, because 4 is 2 squared. 1 times 8, 2 times 4. 1 times 16. 0 times 32, and 1 times 64. Because now these are powers of 2. Powers 0, 1, 2, 3, 4, 5, 6. So what's the value of this binary number here in particular? In decimal, we get the number by summing this stuff here. So we have a 0, we have a 2, we have a 0, we have an 8, we have a 16, we have a 0, and we have a 64. These guys give me a 10. These guys give me an 70, 80. So this number looks like a 90. Let's ask Python. So it is correct. We have a 90. So internally on the computer, all the values are always stored in binary, because it's actually just like electromagnetic stuff, like bits are either on or off, and anything that's stored on your computer is stored in this manner, on or off. So when we're looking at a number like, let's say 54, on the computer, we're actually storing 1, 1, 0, 1, 1, 0. What are these 1, 1, and 0? There's a 32 there. There's a 16. There's these two ones here. 8 isn't there. 4 is, 2 is, 1 isn't. That's the 54. The 0b just means it's a binary number. So I can do all kinds of things with these bits. I could, for example, take a 14 and I could make a logical AND with a 23. And that would be a 6. Okay, now, what the fuck? Let's find out. Bits of 14 are 1, 1, 1, 0. Bits of 23 are 1, 0, 1, 1, 1. Let's put this in an editor. So we had a 1, 1, 1, 0, that was 14. And I have a 1, 0, 1, 1, 1, that's 23. And I was doing an ampersand, which is the logical AND. An AND means 1 if both are 1, otherwise 0. So when I do this operation, First, I need to imagine that these numbers have the same length. Zeros in front of a number don't change its value, so I can add a 0 in front. It's still the same exact thing. Like I can confirm it here. If I look at what's 1110 base 2 as an integer, it's 14. And no matter how many zeros I put in front, it's still 14. So if both are 1, we put 1. Both are not 1, we put 0. Both are not 1, we put 0. Both are 1, we put 1. Both are 1, we put 1. Not both are 1, we put 0. What does this number stand for? It doesn't have the 32. It doesn't have the 16. It doesn't have the 8. It does have a 4. It does have a 2. It doesn't have a 1. So it's a 4 plus 2, which is a 6. So 14 and 23 values 6. We can also do an OR. Let's do the OR for the same numbers. OR is just a bar. That gives a 31. Okay, let's copy this stuff and see why the OR is a 31. So now we're going to do an OR. And an OR is only 0 if both are 0, otherwise it's a 1. So we're going to have 1, 1, 1, 1, 1. Great. All these ones are going to give a 31 because it's going to be a 16 plus an 8 plus a 4 plus a 2 plus a 1. Or we could do this. This is an exclusive OR. Let's copy. XOR wants them to be different values, so it gives a 1 if only one of the inputs is 1. If both are 1, it gives a 0. So it's going to be a 1, 1, 0, 0, 1. So what do I have here? I have the 16 and I have the 8 and then I have the 1. So I have a 25. There's some wind. I hope I won't lose power because everybody knows how stable the power grid is. Let's take a screenshot quickly before Comisión Federal de Electricidad decides that we don't work anymore today. So now these are bitwise operations. So AND is really good at forcing bits to be 0. Or maintaining bits, like if you make an AND with all 1s, everything's going to stay the same. If you make an AND with all 0s, you're practically wiping the 1s out. If you make an OR with all 1s, you're making everything 1. If you make XOR with all 1s, you're effectively flipping the bits. There's all kinds of funky things you can do with this. And we often as programmers need to do all kinds of funky things with this. 2 more operations you need to know are the bit shifts. I could take a number, let's take a 5, and push it 3 positions to the left. Or let's take a 16 and push it 2 positions to the right. What's going on here? If I look at the bits of the 5 and then I look at the bits of the 40. A 40 is a 5 with 3 new zeros added to the end. So that's what this thing does. It adds 3 new zeros to the end. It's pushing the 5 3 times forward. And now since we're in base 2, every time a digit moves to the left, it gets multiplied by 2 because it becomes the next power of 2. So the first 0 we add, the 5 becomes a 10. We add a second 0, that 10 becomes a 20. We add a third 0, the 20 becomes a 40. So when we go the other way around, when we take 60 and I take away 2 bits from it, it's like I'm dividing it by 2 twice. First it goes to 30, then it goes to 15. Then if I take more bits, that 15 is going to go to a 7 because it's not going to go to 7.5. We've lost the decimals. If we take 4 bits, it's going to go to a 3. If we take 5 bits, it's going to go to a 1. So these things are the shifts. We can add P zeros to the end of x, or we can remove the last p bits of x. So this is stuff we can do with binary values. I'm actually going to rename this to, let's call it bin.txt. Let's add it to the Git. Git repository gets it. Goes in the Gits. There we go. And now we should be in condition to look at the last exercise we were going to do, which is this one here. Write a function set bits that returns x with the n bits that begin at position p set to the rightmost n bits of y, leaving the other bits unchanged. Okay, so let's try to understand this. So if I have an x that could, for example, be 1, 2, 3, 4, 5, the bits of x look like this. Okay, the n bits that begin at position p. Okay, so now if I get a p, that would be a binary position, like let's say 3. So now technically, since we're in Python, we could do easy things here. I could just, no, actually, let's be okay with this. If these are the bits and this is p, how do I get the bits that begin at position p? So this is position 0, this is 1, this is 2, this is 3. So if I take x and I push it p positions, no, the other way around. If I push it to take away b positions from it, I can't type, going x pushed by p. So now I first had this, and I've taken away the 0, 1, and 2 positions. So now I only have the start from position P onward. Okay, so I want the n bits from there. So what are the n bits that begin at that position? Let's take an n, like let's say 5. So now I don't want the beginning stuff. I want the end stuff. How do I get rid of beginning stuff? I get rid of beginning stuff by making an AND with ones in the part that I want to keep. How do I make ones for the part that I want to keep? I could take a 1 and I could push it n positions forward. So I could get 1 and 0 zeros at the end. Then I could negate this. And this is a funky little thing. I can negate the bits, and in Python this is not going to work exactly as I want. In C it's going to work wonderfully. It's mostly broken here because I'm seeing as a negative. I would flip the bits so all the ones become zeros and all the zeros become ones. So just imagine here a 0 and here ones. So if I would AND those with the x, it means that I would only keep these because they would be ones, and I would nullify the others. So let's see how this goes. If I take the x pushed by the p and I AND it with the negation of the 1 pushed by n, AND it with just one AND though. There we go. What are the bits now? So I wanted to skip those, and then I wanted to keep the next 5. I wanted to keep these 5, but I wanted to get rid of those. So now my AND's not working as I wanted to. I wanted zeros in the end. I wonder if this works in C like I wanted it to. How do I make the negation work like I want in Python? Let's Google. Okay, it's best we do this in C because doing it in Python is going to confuse you guys horribly. So let's try to start moving the stuff to C. Let's make a bit stuff C. So we wanted to make a function set bits. It was going to take an integer x, an integer b, an integer n, and an integer y. And we had already argued that we wanted the bits at position P set to the rightmost n bits of y, leaving the other bits unchanged. So we first need to store away those beginning bits of x so that nothing happens to them. So if I have these bits of x and I want to, leaving the other bits unchanged, n bits that begin at position P, set to the rightmost n bits of y. Okay, how do we get the rightmost n bits of y? Okay, so if this is n is y is this, and we want the rightmost, so these ones here of y, we would need to keep these bits and get rid of all the other bits. So we want the 1 pushed by n. It's going to be the mask that has zeros in the last n positions and a 1 before that. So now I would essentially need those zeros to become 1s, and then I need to get rid of the others, but I also need to get rid of the former ones. I hate thinking while I'm streaming, because I can relatively easily flip those, but then all the others need to be 1s, and it's easier in C because there's a fixed length to it. So basically we could first have a 0, and if we invert that 0, we should only have 1s. So if you have only 1s and we want to keep the 5 last ones, we could make first a thing that has only 1s, and then maybe we could push those to put the 5 zeros and then flip it. Because what we need is a mask that needs to look like lots of zeros and then 1s for the n's. So we basically just want to put the n times the 1. So we could make the mask be 1 first. Then we could, while, that's a 4. Let's do an int I here. While I is 0, I is smaller than n, we increment I. We are going to make the mask be that mask with a new 0 at the end, and then we sum a 1 to it. Okay, so if n is 5, our mask is first going to be a 1. Then what I would do here in Python notation, for I in range n, mask would become mask. Okay, let's look at what mask looks like now. Okay, I made 1 too many. I made 6 1s because there was a 1 there. So if we would start with a 0, we should get the 5 1s. Okay, so we have 5 1s now. Marvelous. So now what we want to do, we want to take those bits of y. So I want to nullify all the other bits of y. So let's make a thing called keep. Keep is going to be this mask in an AND with y, because remember, AND only keeps the ones that are 1 in both. So if I have y that looks like this, and I have the mask that looks like this. Now the mask and y will only keep the last 5 bits of y. Everything else is going to be wiped out because they weren't there. So now we want to get the bits that begin at position P in X, and we need to put these bits there. We need to override whatever bits were there. So first of all, I need to maybe make a 0 on all those positions for X. So let's fix the mask a little bit, because now the mask is the 5 ones. And if P is 3, we need to push it forward. So we need to now push the mask P positions forward. So if I take a mask and I push it by P, I get this. So this is going to be my new mask. And now in my bits of X, I need to replace these bits by the bits of Y. All the other bits need to stay the same. So I'm thinking that if I make a XOR, all the original bits that were 1 in X are going to continue being 1s in the result. The ones that were 0 will continue, they will become 1s because there's a 1 in here. And if there were any 1s in here, those will become 0s. So I would just flip those bits if I do the XOR. I don't want to flip those bits. I want to force here the bits that I take from Y with the mask. The easiest way would be making these all 0 and then ORing with Y. Because if they were all 0, then ORing with a Y would make it okay. The easiest way to 0 them out would actually be pushing them out entirely and then putting these ones back. So we could do that. We could copy the original X into another one. Okay, let's try that first. Let's do an original. We'll copy X there so that we could modify the X by taking away the last P. Because if we take away the last P, then we could just put the ones we kept at the end of it, because we can push X back by P positions to create all 0s. And if we've created all 0s, then we could OR the X with the ones we keep, meaning that we should be holding on to the bits from Y. Let's try this. So if I make an original, that's a copy on X. And first I get rid of some bits on X. So what was originally X looked like this. And what X is now, it looks like this. So I've taken the last 3 bits away. Then when I push them back, they are now 0. And after I push them back, oh no, but I wanted to replace the... Okay, I need to push more away. I need to push away the P plus the N, because I want to take from position P onward and replace the N. Okay, so let's take away the Let's put x back to the original. Let's take away the p plus n. What's it going to look like? It's going to look like this. Because we took away these 3 and then these 5. So x is going to be replaced by a version that's pushed by p plus n positions. Then we're going to put those positions back as zeros so that it has the same length as it had before. Now we could make an OR with that and the keep. We never stored keep here. Keep was supposed to be the AND of mask and Y. Going back a little bit to check this. Oh, but we changed the mask. We changed the mask. The keeps are not the correct ones anymore. Let's go back to the original mask. So the original mask was first 0. Where's my 4? This is the mask I wanted, so keep would be the mask and the Y. These are the bits I wanted to keep. So now if I would take the OR with the X and the keep, I would now have those there. But I need to remember, I don't want them at the end. I want them at the position P. So I need to move them P positions forward before I put them to X. And then my problem is restoring the original last bits to X. So now X has only zeros at the end, and I only want the last P positions. So what's the easiest and simplest way to do this? I'm probably going to do a weird cluster that would be simplified very easily. But we now have the bits that we have taken. We want the last B bits to be matched, so we could just do another 4. We could go, I could go from 0 up to P. Let's make it a little complicated here, so that, well, a little long really, not really complicated. Let's just look at those bits. So now we want that if in original we have the bit on, so if original we have a 1 at a position I, if that's true, if there's a 1 there, then we want X to have a 1 there as well. So we're going to OR X with the, let's actually put this in mask. It's just one single I, one single 1 in position I. If it's set in original, let's make it a little clearer here. If original and I is larger than 0, so like if there's bits in common there, then we want to add that to X as well. If it was a 0, then we don't want to put it in X. So maybe this would work. And we didn't need to negate anything, so we could actually try this on Python. Let's quit it from here, write the same thing in Python. So we have a set bits that has an X and a P and a Y Okay, the same order as here. Original is going to be X. No, X. Mask is, I'm just going to call them O and M, is going to be 0. So now keep is going to be the AND between mask and Y. X is going to lose the P plus N. Let's put that in a variable. Total is P plus N. It's going to lose those bits. Let's put parentheses here. So we're going to nullify those bits. And then we're going to put them back as zeros, so the length is the same. Then we are going to take the OR between the bits of the keep, but they need to be pushed P positions forward. Then for E in range P, we want the mask to be 1 pushed by I. If original and I give some bits on, then we need to OR the mask into X, and then we would return X. And we could test this in Python relatively easily. Let's make an interactive Python here. Okay, so let's try this now. Let's put an X, let's put a Y, let's put a P, and let's put an N. So then the result would be set bits X, P, N, Y. Oh, orig is supposed to be just an O. I have to quit and come back because I need to reload it. Okay, and now let's see what we have here. We have bits of X. Test txt. Let's copy them here. These are the bits of X. Okay, let's look at the bits of Y. These are the bits of Y. Make them the same length so we can understand this. So this is X and this is Y. Now, N and P are 3. So the positions here, these are positions 4, 3, 2, 1, 0. So we wanted from position P, P is 3, so this is where we're cutting, and we want N bits from there, so N is 4. So we're wanting to take the N bits that begin at position P, set to the rightmost N bits of Y. So it means that this stuff here is supposed to be replaced with this stuff here, right? So we're supposed to have 1, 0, 0, 1, then we're supposed to have 1, 1, 1, 1, and then we're supposed to have 0, 1, 0. Because we're supposed to keep those 4, replace those 4, and keep these 3. So that's what we're supposed to be doing. So what does the result look like? 1, 0, 0, 6 ones, and then some cluster there. Okay, so this is not looking exactly as it should. What we have here is a good start, but there's something wrong at the very end. So where's the part that's wrong? Let's analyze. Let's return it before we add anything to the end and just ignore this part here. And let's add our testing into the file so that we can run it from the file. That's Y, that's N, that's Y. And we really just want to be looking at these bits here. First, let's see if my manual work is correct. So I'm supposed to have 1 0 0 1, then 4 ones, and then a 0 1 0. So that looks like that should be okay. Let's quit here and run the file. N's 4 and P's 3. Okay, I think I have the correct values now. So 1 0 0 1, okay, and then the 5 ones. That's fine. So the only part where we have trouble is at the very tail. So the last P positions, what do the last P positions look like? In the original, if I'm looking at the very last position, let's look at this. If the very last position is a 1, if the zeros position is a 1, I want to set a 1 in the zeros position. And O is the original value of X. So why did it go like 1 too far? So this should go first 0, then 1, then 2, since P is 3. So this thing should give me first a 1, then a 1 0, then a 1 0 0. And if we're ANDing it with the original, and the original ends in 0 1 0, we should first be looking at the 0 1 0 versus this, and it should give me that that's a 0, the AND. Then it should be 0 1 0, comparing with 0 1 0, it should give me a 1 here, so it's a 2, so it's larger than 0. Then the 0 1 0 with the 1 0 0, it should give me the 0. So let's just print something out to see what's going on. So 2 is the one that's on. Zero 1 0 is supposed to be X to put onto X. So weird. No, but 2 is on, it's too far. Okay, it's too far because it's not the 2, we want the 1 to be on. Let's print the binary representation of the mask to debug my... Okay, so 1 0 0 is the one that gave it on. printing the bits of the original to look at them. 0, 1, 0. Okay, that should be correct. Oh, I'm doing O and I. Guys, help me. It's O and M. Okay. So now our Python should be given exactly what we wanted. So we should be in condition to check if our C does the same. So now actually in the Python, let's stop printing the bits and start printing the integer, since we now know it's working, so that we can easily compare with the integer it's going to give us on the C, so that we don't have to write a code that actually prints us the bits. That's a good exercise, but we don't necessarily want to do it. So now let's look at the bit stuff Python and make sure that we have the same logic here. I don't need these comments anymore because I know what's going on. So we have the original, we are building the mask, we're keeping the mask and the Y, we're pushing the bits out, we're filling them with zeros, we're getting the ones we keep. Here we have the same exact error, original with mask, we should put those on, so that then we could return the value of X. And if we want to test this with those same values, let's write here a main. We need to include stdio to print stuff out. So I want to print out set bits for 1, 2, 3, 4. P is 3, N is 4, and Y is 5, 4, 3. And we probably also want to print an enter, so that's going to be an integer followed by an enter. Let's see if this compiles. It's called mask in the C code. And we need the parentheses to first do the and then compare with the 0. 1, 2, 7, 4. Yes. Okay, so this seems to be reasonably doing like what it's supposed to be doing. We're going to commit it as exercise 2.6. At this point, I would like to share with you guys that when I first tried to learn this binary level stuff, I thought I was the dumbest person on the planet and I would never understand it. Then it kind of like dawned on me like a divine illumination what's going on here, after spending a lot of time with a notebook writing numbers in binary and trying to work these things out. And this code will probably come to me tomorrow morning at 4 a.m. as a 4-line version, a much shorter way to do the same thing. And the better you get at this, the easier it becomes to write this code. It's going to take a long time. It's not going to be easy this week, but you need to try it this week, because if you don't try it this week, you're never going to be good at this. Because the sooner you start trying, the sooner it becomes natural. So let's go look at quickly the at the mini exercises for chapter 2 and the big exercise for chapter 2. So we are now at types, operators, and expressions. Here, the very first one has to do with this representing numbers in bases that we were just talking about. And I would really want to give you guys a hint of looking at the example for logarithms for discrete math. I'm just going to copy it from there. If you don't understand logarithms, you're not going to understand this exercise. Please discuss on the channel when you get confused. So this time you're not going to put me what the program prints. You're going to put me what code needs to be put here. It's really important you put your number be here. In A, you can put any arbitrary non-negative integer here. In the second program, you're also going to write a little bit of code. You're going to put your k in here. You're going to put any non-negative integer in here. So just try different values here. And write me what needs to be written here so that the program does what it's supposed to. So we need to force the bit at position k to 1 and the bit at position k divided by 2 to 0. So forcing bits to 1 and 0 is this thing about using the ands and ors that we were just looking at in the examples. And in the third one, we're practicing the mini-if, the thing where you have the interrogation sign, the question mark, and then an option and like a colon and then another option. That's what we're practicing here. It's going to go in here. We're also practicing including the math functions. So please, when you get confused, discuss on the channel. Again, do these 3 before you start working on the programming assignment. They are notably harder than last week, and you actually need to understand chapter 2. If you get confused with this binary representation stuff, with representing numbers in bases, with the mini-if thing that already has an example, it's under the chapter 1 examples. It's actually literally called miniif.c. So look at that thing for the third one. And now let's look at what you're supposed to program. Having concluded the above stuff, you will write a program. You don't borrow any code from anywhere. It's going to print out the binary strings corresponding to the first k prime numbers. Okay? You will define k as a numerical constant in your code. So k could be like 20 or 50 or 100. So you're going to be printing out the prime numbers. So like the first 5 prime numbers would be 1, 2, 3, 5, and 7. Those are prime numbers because they're not divisible by any other number. So obviously you're going to need a program that determines whether or not a number is prime so that you can figure out which ones are the first k prime numbers. So make a subroutine that looks for prime numbers. Then you make another subroutine that takes the number and makes the binary string, the zeros and the ones, corresponding to that number. Then you need to figure out how many bits is the largest number going to have, because the largest number could have like 12 bits. So then the one that's going to be the first number, you're not just going to print 1. You're going to print 11 zeros and a 1. And for the 2, it's going to be 10 zeros and a 1 and a 0. For the 3, 10 zeros and a 1 and a 1. For the 5, it's going to be 9 zeros and a 1 and a 0 and a 1. So I want all of them to be the same length. I will type this in a file so that we don't panic. Let's just call it output, what the output should look like. So the first prime numbers are the 1, 2, 3, 5, 7. Let's just do those. Actually, let's do a little more. 11's prime, 13's prime. So let's do those. 1 in binary is just 1. This is 1, 0. This is 1, 1. 1, 0, 1. 1, 1, 1. 11 would be an 8 without the 4, but with the 2 and a 1. And a 13 would be an 8 and the 4 and not the 2 and the 1. Okay? So now these are the first 7 prime numbers. in binary, but they're not all the same length. Now they're all the same length. So your program is supposed to write this. If you give it a 7, it's going to spit out this. So please subroutines, one for figuring out whether a number is a prime, one for making a binary string, and a third one for making the length of the binary string be a fixed value. And if you understand this exercise well, you will know how many bits the largest one's going to have. But I would probably first look for them and then print them, or you could print them and try to like estimate how long the longest one's going to be. And I don't care if you have too many leading zeros, but I will care if you have too few. So I'm not going to be mad if your output has 1 extra 0 here in front or 2 extra zeros here in front. I'm not going to be mad. But I am going to be mad if some of the strings are shorter than others. So that's homework 2. And now we have 5 lovely minutes to look at what should have happened in homework 1. So let me actually make a new one here. Let's go back to chapter 1. So the homework 1 is very close to the no comment one. So I'm just going to copy the no comment one. Let's rename it homework 1. I'm not going to do the whole thing because I don't want to ruin it for everybody. So let's just make a relatively stupid one here. We're not going to ignore anything. We're going to have like a boldface option. And we're actually going to want to iterate over the length of the line. So here we're going to do, let's do an I. I goes from 0 to L, because L is the length of the line. We're actually probably want to go, no, we're just actually going to modify this thing. We're just going to do it in the subroutine. Let's get rid of the subroutine. Let's make this much easier. We don't need the SC either. Let's just first do the tag thing. So when tag starts, we're going to start skipping. When tags end, we're going to stop skipping. If we're not skipping, we're going to put the character. Let's look at this first. This is the version of what we could be doing. So I don't really need this. I'm using the max, I'm using the C, I'm using the I, I'm using the skip. Let's see if this compiles. Skip false, I keep forgetting it's C and not Python. I'm not actually using the this at all. C is going to be the get char, and we're going to be doing until it's an end of file. Something's not closing right. This thing here. Okay, so now the bad thing is that it prints the outer one here, so we should maybe put this to an else if. This could also actually be an else if, because it won't be both. Compile again. Okay, it looks lovely. It's getting rid of the tags. And now we just want to react to some tags in a special way. So we could do a thing that would be the boldface, for example. We're also going to suppose it's on false. And if we start skipping and we find stuff that corresponds to the headers that we're interested in, we could turn bold on. Is it called space or is space? Let's look here. Actually, let's just use just the white space as such. If C is a space and bold is on, we're going to actually do a put char of the underscore. In and other cases, we're going to put char of the C. When do we put bold on? Let's make a crude hack of this thing. If skip is true, so if we are skipping and we are inside a tag, let's say that if we're inside a tag and we find an H, we would put true on. And we could make a very stupid version here where we would turn the bold off whenever a tag closes if the bold was on already. So, well, basically, no, we want it to stay on for the beginning tag, but we want it to close when there's a closing tag. How do I know if there's a closing tag? Closing tags are the ones that have the slashes. So we could make a if C is a closing tag. No, it's not that slash, it's this slash. Then we could turn the bold off. This is a very dumb version. So if we're skipping and we find an H, we start using bold. And then when we are closing the tag, we always turn the bold off. So let's try this. Let's see how badly I've broken it. Okay, the bolt didn't go on, so we were in skip was true. And we should have had a character that was an H. Oh, because, okay, it's inside here. So it can't be in an else if not skip. It has to be in an else. Because else if not skip takes everything that's already skipping. So if we're skipping and we encounter an H, we could turn the bolt on. Let's try again. My cats are losing it because I'm 3 minutes late for feeding them. Okay, the bolt went off on when it was supposed to. It just didn't go off when it was supposed to, because we're also putting the turning the bolt off in the non-skip. Whereas it should be here in the skip. Let's try this version. Low, I'm still not closing it correctly. So if it is this and skip is, oh, but we already turned skip off, because this is where we turn skip. No, this is where we turn skip off. So skip should still be on when we're in here. So skip is on, and we should encounter a slash that should make bolt false. False is a 0. Anytime we encounter the slash, we should turn it off. So it should have turned off here. Oh, well, I'll fix it and then I'll upload it. And I figure out why it's not closing where it's supposed to. But this is like a very quick hack of only reacting to some of the tags. But I only had like 5 minutes to do this. So let me close the stream, come to Discord if you have any questions on voice, because we're extending the hour here. I'll fix this while I talk to you guys, and I'll upload it as a quick hack of what you were kind of supposed to be doing.